In section 4, we're going to talk about angles in circles. So first we're just going to review what a central angle is, and how you find the measure of a central angle. So in order to find the measure of a central angle of a circle, you take the length of the arc and divide it by the radius. So if we're looking at what that looks like, so we have our circle, we have, our radius, our two radii, we have the arc. We want to find the measure of our central angle theta. So to find the measure of theta, we want to use the arc length formula. The length of our arc S, and we want to divide it by r, the length of our radius. And because we want our angle to be in terms of degrees instead of radians, because if I leave it like this, the length of my arc is divided by my radius, this would give me an answer in radians. So this is the formula if you want the measure of your angle in radians. But if you want it in degrees, you have to do S divided by R, and you have to multiply it by 180 over pi. And that's if you want the measure of your angle in degrees. So it's just one extra step if you want it in degrees versus radians. So it's a fairly easy formula. Just divide the length of the arc by your radius, and that will give you your central angle. And it comes directly from the arc length formula. Because if you remember, our arc length formula is the S equals R theta. So if you want to solve for theta, you just divide both sides by R. So that's where the formula comes from. And since theta is already in radians in the arc length formula, that's why the initial formula is also in radians. Okay. Now we're going to start talking about angles inside circles. And there's two different angles inside circles. We have something called an inscribed angle, and then we'll go back to angles formed by intersecting chords. So if you're looking at an inscribed angle, it is an angle formed by two chords that have a common endpoint on the circle. So if we're looking at a circle, we draw our two chords. The endpoint is this point A on my circle. And then we have where it ends, B and C. So my inscribed angle is this angle theta. It's the one that's on the inside. So the way you find the measure of that angle, theta, is it's half the measure of its arc. So in this case, its arc is BC. So whatever the measure of arc BC is you do half of that, and that gives you the measure of angle A. So when we're trying to find the measure of that arc, you think in terms of the center of the circle, which I'll call D. So what you do is, if you know, draw my angle here, whatever the measure of this angle is the same as the measure of the arc. So whatever the measure of the inscribed angle is, the central angle is, that's the measure of the arc. So if this were 65 degrees, the measure of my arc would be 65 degrees. And then it would take half of that, and it would give me the measure of my angle A. Next, we're going to go back to intersecting chords. So we talked about the relationship between the lengths of the intersecting chords, and now we're going to talk about the relationship between the angles formed by the intersecting chords. So it is angles formed by two chords intersecting. So if in a circle you have your two chords, we'll say AB and CD, and you can pick any of the angles formed. So So there are technically 4 angles formed by 2 intersecting arcs. So you just need to pick one of them. So like if I wanted to find the measure of this angle theta, what I do is I do half of the sum of its intersecting arcs. So the intersecting arcs are AC and BD. So it's very, very similar to the formula for an inscribed angle. It's just that you have to add whatever the 2 arcs are on either side. And then you do half. So very, very similar to an inscribed angle. The last thing we're going to talk about is when angles meet outside of a circle. So far, the only thing we've talked about is angles inside the circle, but there are angles formed outside the circle. So an angle whose vertex is outside the circle and the sides are tangent or secant. So those are 2 new terms here that we haven't discussed before, and they are different than the trig terms, tangent and secant. So you know, sine, cosine, tangent, and then there's secant, cosecant, and cotangent. Not the same definition at all when we're talking about triangles. They have their own definition when it comes to circles. So in a circle, a tangent is a line that touches the circle at one point and is perpendicular to the radius. And I'll draw some pictures here in a little bit so you can see what it looks like. A secant is a line that touches a circle at 2 points. So there's 3 different ways you can have angles outside circles. You can have 2 tangents, 2 secants, or you can have a tangent and a secant. And the nice thing is, no matter which type you have, the formula for calculating that angle is the same no matter what 2 you have. So we'll start with if you have 2 tangents. So if you have 2 tangents meeting outside a circle, you have your circle. So a tangent line only touches the circle in one place and is perpendicular. So let's see if I can draw. So here's the point where it meets the circle, and it does form a 90-degree angle with the radius. So that means my radius goes directly here, and I have a 90-degree angle here. And if I have a second one, again, meets it, I draw my radius, meets it a 90-degree angle. So I have my angle A, and then the angle that's formed is this angle theta. And what I care about are the arcs created by those 2 tangent points. So I have one on the outside, and I have one on the inside. We'll call this B, and we'll call this C. Next, I'm going to draw 2 secants. Again, have a circle. I have my angle A, and it meets the circle at 2 points. So I have my angle theta, and similar to when I had 2 tangents, I have my outside arc, B, and I have an inside arc, C. And then the last one is 1 tangent and 1 secant. We have our secant and our tangent, our angle A, 1 point, 2 points. So my angle theta and then my outside arc, and my inside arc. So in every single one of these cases, the formula to find theta is to take whatever the measure of arc B is minus the measure of arc C and divide by 2. So whether or not you have 2 tangents, 2 secants, or 1 tangent and 1 secant, it's always the measure of the outside arc minus the measure of the inside arc divided by 2. All right, so let's go ahead and do some examples. So we're going to find the measure of either an inscribed angle or a value of x for the different ones we've talked about. So for our first example, x, if we look in our example, we have an inscribed angle here, which means x is equal to half the measure of its arc, which has a measure of 102. So x is going to be equal to 51 degrees. We can also go backwards. If we know the measure of an inscribed angle, we can use that to find the measure of its arc. So 23 is 1/2 of my arc x. So to solve for the measure of my arc x, I'm going to go ahead and multiply both sides by 2 to get rid of that 1/2. And we get that x is 46 degrees. So let's go ahead and solve for a variable here. So I have the measure of my inscribed angle. It's 2x plus 6. So I need to set that equal to half the measure of its arc. So if I look at the arc formed by that inscribed angle, it is the diameter of the circle. And a diameter of a circle is half of the 360. So that means 2x plus 6 has to equal half of 180. So that means 2x plus 6 has to equal 90. So we'll subtract 6. We get 2x equals 84. And then we'll divide 84 by 2. And we get x equals 42. I don't need to have degrees here because I didn't actually solve for the measure of the angle. The angle I already knew. The angle is 90. What I did was I solved for the variable x. The first 2 examples I solved for, I actually solved the measure of the angle or the measure of the arc. So I had to put degrees on the answer. In our next example, we have 3x plus 7 and 6x minus 11, and we want to solve for the value of x. So if I actually follow the chords for each of my angles, what I'm going to notice is that each of those angles intercept the same arc. And if 2 inscribed angles intercept the same arc, they have the same measure. So because those both intercept the same arc, that means that 6x minus 11 has to equal 3x plus 7. So I'm just going to solve for x. So I'm going to subtract 3x. So 3x minus 11 equals 7. Add 11 to both sides. We get 3x equals 18. Divide by 3, and x equals 6. All right, so number 5. Looks a bit complicated because we're going to be solving for 2 variables here, x and y, but it's really not so bad. So for my first inscribed angle, my 30-degree one, the arc that it intercepts is x, so that tells me that 30 is 1/2 of x, so I'm going to multiply both sides by 2, and we're going to get that x is 60 degrees. for my angle y, so even though they share a chord, they both share the same chord, they don't share the same arc. It goes with the arc that measures 98 degrees. So we know y is going to be 1/2 of the measure of its arc, which is 98. So then we do 98 divided by 2, and we get that y is 49 degrees. So even though it looked kind of scary to begin with, you treat them separately, really wasn't that bad. All right, so let's look at examples of tangents and secants. So in our first example here, we have a tangent and a secant. Doesn't matter though, because the formula is the same. X is going to be the measure of the outside arc, which is 120, minus the inside arc, 32, divided by 2. So our outside arc, and then our inside arc. So 120 minus 32 divided by 2 tells us that x is 44 degrees. Sometimes we are going to be solving for, we might have to do some work to find the inside or outside arc. So even though x is kind of not labeled as great in this next picture, it is asking us to find the measure of the angle. It's just that because the secant and the tangent meet at such a small angle, it's labeled more inside the circle. But we have the measure of our outside arc. It's 144. We don't have the measure of our inside arc yet, so I have to solve for it first. And the nice thing is, I know the other part of my circle. I have 187 is the measure of the arc that is not between my tangent and my secant. We know all of the degrees in a circle are 360. So I do 360 minus 187 minus 141. And that's going to tell me that my inside arc has a measure of 32 degrees. So when I go to solve for x, it's 141 minus 32 divided by 2. So 141 minus 32 divided by 2 tells me that x is 54.5 degrees. And you are going to be able to write decimals for these because we're not necessarily guaranteed a whole number. It'll be the real whole number or something that's a 0.5. That's the nice thing. So let's go ahead and look at an example where we use the formula. We know the measure of the outside angle, but we want to solve for either the measure of the outside arc or the inside arc. So in this example, I know the measure of my outside angle is 46. We know the measure of our outside arc is 134, but we don't know the measure of our inside arc. So when we set up our formula, we know 46 has to equal 134 minus x divided by 2. So my first step here is going to be to multiply both sides by 2 to get rid of my fraction. 46 times 2 is going to give me 92 equals 134 minus x. Next, we're going to subtract 134. And it's okay here that we're going to get a negative number. You should get a negative number in this case. We get negative 42 equals negative x. So then our last step is to divide both sides by negative 1. So we get x is 42 degrees. Okay, so let's do an example where we solve for the outside arc. So we don't know the measure of our outside arc. It is x. We know the measure of our inside arc is 66, and we know the measure of the angle, our outside angle is 42. So we'll have 42 equals x minus 66 over 2. So very similarly, my first step is going to be to multiply both sides by 2. So we're going to get 84 equals x minus 66. And the nice thing is, it's a little bit easier to solve for an outside arc, because then I'll just add 66 and we'll get that x is 150 degrees. So it is a little bit easier to solve for the measure of an outside arc if you know the inside arc and the outside angle than it is to solve for the inside arc. But it's just one extra step. It's not like it's a lot more complicated. All right, let's go ahead and for our last example, do an example where we solve for our variable x. So I actually have measures for my outside angle and my inside angle. I just have them in terms of x. I don't actually have them in terms of degrees. So we know the measure of our outside angle is 30. And if I use my formula, that's equal to 5x plus 10, which is our outside arc, minus my inside arc, which is 3x plus 4. And I do have to put 3x minus 4 in parentheses because I have to subtract the entire thing from 5x plus 10, not just the 3x. And then, of course, it's all over 2. So my first step is going to be to distribute that negative. So we get 5x plus 10 minus 3x minus 4 all over 2. Then I'm going to go ahead and combine like terms. I'll move up here to finish it. So we get 30 equals, and then 5x minus 3x is 2x. 10 minus 4 is 6 all over 2. So I have two choices at this point. Because 2 and 6 are both even numbers, I can divide them by 2, so I can go ahead and divide them by 2. But since that's not always guaranteed to be the case, I'm going to go ahead and just like if we were solving for one of our arcs, I'm going to multiply both sides by 2. So I get 60 equals 2x plus 6. And now I'm just going to solve for x. So I'm going to subtract 6. We're going to get 54 equals 2x, then divide by 2, and we get x equals 27. So that was one of the options. The other option to solve for x here is I could have just gone ahead and divided the 2x and the 6 by 2, in which case I would have gotten 30 equals x plus 3. Then I subtract 3 from both sides, and I still get that x equals 27. Both are valid methods, but like I said, it's not always going to be the case that when you combine those like terms in the numerator, you get two even numbers. So you have to be able to do both methods in case I've gotten like 2x plus 7, in which case 7 is not divisible by 2 nicely, so I want to make sure that I'm not dealing with decimals as much as possible. So let me know if you have any questions about angles and circles, whether it's inscribed angles, angles formed by two chords, or angles outside of a circle in terms of tangents and secants.